All right, hey AP Chemist. This is going to be important information part 4, and this is our first video lecture. We're going to be looking at writing and balancing chemical equations. So this is a big important information unit here. So up until now, we've learned about elements, compounds, and mixtures and pure substances. We've done things with the mole and calculations for percent composition. And now we're going to be focusing our way with applying all of that to chemical reactions. So when we have a chemical change or a chemical reaction occurring, we typically represent it with a chemical equation. So here is a chemical equation right here. Okay, so this is a chemical equation for something called the combustion. Combustion typically means like you burn in air. Combustion typically is like what happens inside your engines, but combustion of natural gas. So here's CH4, I add it to O2, and I get CO2 and H2O as products. Now this arrow right here, this arrow in the reaction arrow, that's read as yields, like I'm making it, or it produces. Sometimes you might even hear or see decompose, like whatever I start with is going to break apart. Substances on the left side of the equation are known as reactants. Substances on the right side are known as products. And as you can see here, as I've been doing it for the last couple of lectures, I've kind of filled in some notes so you could kind of follow along and write it down as you're seeing it. We often represent the states of each reactant. So when we say states of matter, we say things like solid, liquid, gas, or aqueous. Here are the different states that we have, and I have some examples here. So if something is a gas, it typically has a letter G. So things like H2 gas, Cl2 gas, right? You write the formula of the substance, and then in parentheses you put the state. Liquid, right here we have bromine, Br2 is a liquid, or water is a liquid, H2O, liquid. Solid, put an S, and here's sodium solid and copper solid. And then finally, this last one is not a popular one, meaning not many people know what it is. Aqueous. Aqueous is kind of what it sounds like if you know aqua. Aqueous means I have dissolved in water. So aqueous means it is a solution involving water, right? A solution that has liquid water. And we're going to talk more about solutions in the important information part 5. That's more closer to the beginning of the school year. So things like ionic compounds tend to be solutions. So ionics tend to have that aqueous, right? So I have sodium nitrate here, nitrate with the polyatomic ion, and sodium chloride NaCl. Now a little bit more about chemical equations here. I'm going to let you know that, we can include the states in equations, but for AP Chemistry, it's not a big deal, right? AP Chem, states are not really required. But need to be recognized. Recognize what they mean. Okay? So here's this chemical equation again, and I included the states for everything. But there's now one more problem. Even though I put the states in and it looks like a lot's going on, it's nice and neat here, we have a problem. And to identify this problem, it's going to be important to do some atom counting. So these are my reactants, and these are my products on the right side, and reactants on the left. Think about this. We know from important information part 1, my before needs to be equal to my after. And that's from conservation of matter. And what I mean by before equals after, amount before must equal amount after. So let's see if we have that in this case. In this case, let's see, we have carbon, and we have hydrogen, and we have oxygen. On the reactant side, it looks like I have 1 carbon. I have that little 4 on the bottom for the H means I have 4 hydrogens, and it looks like I have 2 oxygens. But on my product side, it looks like I have, 1 carbon. I have not 2, but 3 oxygens. There's 2 with the CO2 and one with the H2O. All right, now that's a problem. And then hydrogen, there's only 2 of them. So we have a problem. Matter is not conserved. So how are we going to conserve this matter? Well, I'm going to begin to introduce you a way to do this and how chemical reactions actually take place. Let's make a shaded circle represent a carbon atom, an unshaded circle represent a hydrogen atom, and let's just say a big circle represents oxygen. So on my left side, I have a C attached to 4 H's and O2. And I have my C again with 2 O's and O and 2 H's. Now, for a chemical reaction, we start with these reactants, and these reactants are going to combine to make products. I don't just have one set of these reactants, and it's not necessarily that I'll have one set of products. I can continue to have multiple, continuing to cycle and react until I have no more extra and all atoms have been used up. So let's look at something. Looks like my carbons are good for right now. Let's look at hydrogen. All right, looks like I have 4 hydrogens on the left. 1, 2, 3, 4, right here. I'm gonna highlight them. 1, 2, 3, 4, cool, you see that? But I only have 2 hydrogens on the right, just 2. I need more hydrogens on my product side. This is the beginning of how you could begin to balance an equation. If I need more atoms of hydrogen on the right side, hydrogen comes in the form of H2O on the right side now. It is now found in water. So, if I want to begin to conserve matter, I could draw a whole other water molecule. It didn't come from nowhere. We're going to see that this whole other water molecule is going to come from the reaction continuing to happen. If I do this now, I'm going to change the amount of hydrogen that I have. Now I go from having 2 hydrogens to 4. But I also changed something else. I went from having 3 oxygens to 4. Okay? So now it looks like my hydrogens are equal on both sides. We're good. Now I have to look at my oxygens. I have too many oxygens on the product side, and I need 2 more oxygens on the reactant side. Well, where is oxygen? Oxygen on my reactant side comes in the form of O2. I can't just add it like random oxygen atoms. I have to add it in the form of what the chemical reaction is coming from. So I need more oxygen on the reactant side. So I'm going to add another oxygen molecule, O2. And if I do this, now that 2 becomes a 4, and we are conserved. This whole process is called balancing a chemical equation. Balancing a chemical equation. So we just balanced, meaning balancing the matter, we just balanced our first equation together. I love using this particle diagram or diagram way because I don't have to worry about trying to come up with common multiples and least common denominators. I am just drawing matter as it would react or as it would show up and then just counting circles. So keep in mind, we must balance the equation. We cannot change the subscripts when balancing a chemical equation because changing the subscripts changes the substance itself, while changing the coefficients changes the number of molecules. Now, what am I going to do? I'm going to erase all this space here, but you don't have to erase this. I just want to make sure that you can see my work. What am I going to do now? Well, it looks like in this complete reaction, I only needed 1 of the CH4s. It looks like I needed 2 of the O2s. It looks like I didn't touch anything with the CO2, but it looks like I made 1 CO2. And it looked as though we needed to make 2 H2O. These numbers in the front here, and I realize that you probably wrote on top of this, so if anything, you'd be like writing it on the side here. These numbers are coefficients. And we use these coefficients to denote how many of each substance in a chemical reaction is needed for the chemical reaction to completely run. So a really simple way, like I said, to balance the equation is by using particle diagrams, right? So we have balanced our equation. It looks like the coefficients for this reaction is 1, 2, 1, 2. I wanted to remind you of particle diagrams from important information, the last important information part with part 3 important information, but we could have atoms of an element all the same color. We could also have molecules of an element. We could have like doublets the same color, or multiples the same color where they're connected. I could have molecules of a compound, 2 or more color. And of course, we could have a mixture where I have all different types. But this is roughly not really going to be what we're focusing on when drawing. Here are a couple of examples. We're going to do example 2 together, but look at example 1, and I'm going to talk us through example 1 and how it was already done. You're eventually going to have to go from what we call a word equation. You're going to have to remember how to name, and then going from that name to then what we call balancing a chemical equation. So remember, important info part 3 is all the naming. So this said, write a balanced equation for the reaction between solid cobalt-3 oxide and solid carbon to produce solid cobalt and carbon dioxide gas. Well, I already kind of made the skeleton equation here. First step is write a skeletal equation by writing chemical formulas for each of the reactants and products. So cobalt-3 oxide is CO2O3, carbon, cobalt, carbon dioxide. Look at what I did here. I definitely started by drawing out particle diagrams, one of each, and then I kind of went back and forth counting and saying which circle or shape is not in equal amounts on both sides. Draw particle diagrams, determine the number of each reactant molecule you needed in order to make the product with no leftovers. So when I first did this, I was like, okay, I have 3 oxygens, 2 cobalt, but on the right side I only had 1 cobalt. Let me make another one. Then I was good there. And then I went, oh, okay, I have 3 oxygens on the left, but only 2 on the right. And this is where business started happening. I had to add another one of these CO2s for more oxygens. But then if I needed more oxygen, I needed to add a whole nother one of these. And then I added another set of these, of the CO2, and my oxygens were now beautifully balanced. I had 6 and 6 on the left. But my cobalts were not balanced. I needed 2 more. And my carbons were not balanced. I needed to add 2 more of those. So this was a bit of back and forth here. This is just an answer key. And you could try and prove this yourself doing the same thing that I did, or you could work this later. And I counted how many of each substance I needed for the chemical reaction. I needed 2 of these cobalt oxides. I needed 3 carbons. I needed to make 4 cobalts. I needed to make 3 carbon dioxides. I included the states, but they're not really necessary. And so I got 2, 3, 4, 3. A note, kind of like ionic formulas, the coefficients should be simple whole numbers, not divisible. So up here, we had 2, 3, 4, 3, not 4, 6, 8, 6. Be careful. I have seen students in the past get 4, 6, 8, 6, and it's because you miscounted and did the reaction maybe twice. If you do get 4, 6, 8, 6, you would have to take all those, divide them all by 2 to get your actual coefficients of 2, 3, 4, 3. All right, let's do one last example together before getting started on your exercises. So example 2 is a little tough. There's going to be a bit of back and forth. You're going to see here that I'm going to have to go back and forth in order to get matter conserved. So I wrote out the equation from the word equation here. So it was like, when I write a balance equation for the combustion of gaseous butane, combustion again means I burn in air or I add oxygen, C4H10, a fuel used in portable stoves and grills in which it combines with gaseous oxygen to form gaseous carbon dioxide, and gaseous water. We could include the states later. And so I drew one of each. Now, it doesn't matter what atom you start with. I just like to just look at an atom and arbitrarily say, oh, let me try and balance it first. You should balance one at a time. You should balance or make sure you have equal amounts of atoms of each element one at a time, and then you could go back. Never try to balance or never try to conserve two elements at once. It'll get confusing. More than it might already be right now. So my first step here is I like to draw each particle diagram. There were 4 carbons. Here's my 4 circles. 10 hydrogens. I drew 10 small circles that are not shaded as hydrogens. I made oxygen a bigger circle. And here we go. Carbon dioxide is shaded, 2 big circle. Water is H2O right there. 2 little, 1 big. Now I notice that I have 4 carbons on the left, but only 1 carbon on the right. Carbon comes in the form of CO2 on my product side. I'm going to add more carbons. I'm not going to add H2O at this time. If I want to make sure I'm going to balance the carbons, I'm going to add so I have equal numbers of carbons on both sides. Right now I have 1, 2. Here's a third one. And there we go. Here is a fourth one. Now I have equal number of carbons on both sides. That's great. All right, so I have 4 carbons on the left and 4 on the right. For good measure, let's just do hydrogens now. I have 10 hydrogens in here, but I only have 2 on the product side. Hydrogen comes in the form of H2O. If I need 10, it looks like I gotta make 5 of these waters in total. So I have 2, 4, 6, 8. Now I have 10 of those hydrogens. It looks like those small circle hydrogens are in equal amounts on both sides. That's good. Now I have to make sure my oxygens are in equal amounts. On my product side, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I have 13 oxygens. And it looks like I only have 2 on my left side. And oxygen comes in the form of O2 on the left side. So I have to only be able to add O2 at a time. Some of you who might be quick to pick up on the math of the fractions might realize that 2 does not evenly divide into 13. So watch what I do here. I'm going to go, okay, 2, 4, 6, 8, 10, 12, and I have 13 on the right side, so I'm going to have to do 14. So I go, okay, now I have 14 oxygens on the left side, 4 carbons, 10 hydrogens on the left side. On the right side, I'll have 13 oxygens, I have my 4 carbons, and I have my 10 hydrogens. Well, this is why this is tough. I have some bad news for you. We're going to have to continue to balance. We're going to have to add more and do this all over again. So it looks like my oxygens are not in equal amounts. I have 14 on the left, and I have 13 on the right. So how about I add, if I just need to add 1 more oxygen, why don't I just add, boom, right here. I added 1 more oxygen, and now I have my 14 oxygens, but now I have 12 hydrogens. Whew! Now I'm going to have to redo all of this all over again. I'm going to go a little bit faster. If I need more hydrogens now, my only form of hydrogen is C4H10. So I'm going to add another C4H10 and do this whole process over again. Right? Notice how I can't just add 1 or 2 hydrogens. I have to add another 10. Hydrogen comes in the form of C4H10. So now I have to do this whole process again, and let's see if I get there. So my hydrogens are not balanced. Let me get it to have 20, right? Because now I have 20 hydrogens on the left side in total. Those are 20 circles. Right now I have 2, 4, 6, 8, 10, 12. Here's 14, 16, 18. All right, 20 hydrogens. I got 20 hydrogens on the left. We're in business with the hydrogens. Let me do carbons now. I need 4 more carbons because I have 1, 2, 3, 4 carbons here, and I have another 4 there. So the only way I could add carbon is in the form of CO2. Boom, 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 boom. I'm going to put a dotted line because I'm getting a lot of drawing here, right? Now my carbons are good. I have 8 carbons on the left and 8 carbons on the right. I drew that backwards, but you get the idea. Now I'm going to go back and balance my oxygens. I have a lot of oxygens on the right side. Looks like I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. That's a number I could work with in twos. I have 26 oxygens on the product side. I'm going to need to make sure I have a total of 26 oxygens on the reactant side. So right now I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. And now we are in business. My carbons are in equal amounts on both sides. My hydrogens are in equal amounts. My oxygens are in equal amounts on both sides. And we are good to go. Now the last thing we do, now that I know that I'm good to go, is draw in our coefficients. This involved a lot of particles. So I'm going to try and use a different color here. I needed 2 of my C4H10s. I needed 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I needed 13 O2s. I made 1, 2, 3, 4, 5, 6, 7. I made 8 CO2s. And I made 1, 2, 3, 4, 5, 6, 7, 8, 9. I made 10 H2Os. If we check, 2, 13, 8, and 10 are in simplest whole number form. I cannot divide that by any common multiple, so we are good. This is the correct answer. 2 C4H10 plus 13O2 yields 8 CO2 plus 10 H2O. I'm going to let you know this is tough, and this is probably a little bit tougher than AP Chem or what I need you to do, but I wanted to provide in my lecture a tough problem, right? Think about this. If I did all the easy problems in my lecture and I left you with a tough problem, you wouldn't feel so successful. We just did a tough problem together. All right, so now for credit for this work, you are going to complete exercises 1 through 10 and turn them in. If you are good and understand this, you can actually turn off the lecture at this point in time and just work on the exercises. If you think you are struggling, you could stay tuned, and I'm gonna talk through some of the answers here, and do one or two more. I already gave you the answer to number 2, and I gave you the answer to number 6. So if you wanted to pause and copy that, just to keep you going. Notice how in number 6, if I only need one of each, you don't need 1 as a coefficient. Kind of like how we don't have a subscript of 1, like H2O. That O is 1O, but we don't write the 1. So you don't need to write the 1. If you do, not a big deal though. It's not standard. All right, so that's all for this first lecture for the important information part 1. If you have any questions or concerns, feel free to reach out in the Remind or an email. And if you're going to stick around, I'm going to do some of these exercises. All right, so if you've stuck around, I'm going to talk us through exercises 2 and 6, and then I'll probably do exercise 9. All right, so for number 2, it says balance the following equations using particle diagrams. I already did the answer to number 2. It's just 2, 3, and 2. The way that I did this, and I'll redo it all right now since I'm doing it in the lecture. The way that I did this is I just arbitrarily assigned a color shape and circle or square, whatever I want, to each element and I drew out each substance, right? So for N2, there we go. Oops, I gotta make that a little bit smaller. For N2, I draw it like this. For H2, I drew H2 and I drew it as a shade. And then for NH3, one circle, 3 H's. Okay? I'm hoping that you were able to pick this up from my previous lecture, or this lecture where I was drawing and how I drew it, but if not, I'm talking it through right now. So now I look at this and I go, okay, which atom is not in equal amounts on both sides? It doesn't matter which one I start with, but let's say nitrogen, N, right here. I have 2 N's over here, but only 1 here. Nitrogen comes in the form of NH3 on the product side. So I need to add another NH3 if I want to balance those nitrogens. So now I'm good to go. My nitrogens are in equal amounts on both sides. Now let's do my hydrogens. It looks like my hydrogen, I have 2 on the left, but now I have 1, 2, 3, 4, 5, 6 on the right. So I'm going to need to add hydrogen on my reactant's left side until I get the same amount. So right now I added another H2 because hydrogen comes in the form of H2 on the reactant side. Hydrogen comes in the form of NH3 on the product side. 4 isn't enough. I'll add another H2. Boom, there's my 6. I got 1, 2, 3, 4, 5, 6. Now we're good to go. And now we are balanced. I also think I paused for I had a little space here. It looks like I also had the wrong answer for number 2 when you saw that before, whoever saw it before. This should be a 1 N2. Looks like I made 3 H2s. And it looks like, I used 3 H2s. And I made 2 NH3s. And we are balanced, right? And again, these coefficients come from, these coefficients come from here, where I go, 1, 1, 2, 3, 1, 2. Done. All right, so you could do exercises, hopefully 1, 3, and 4 on your own now. Let's look at 5 through 10. 5 through 10 is a little bit tougher. It's important. You'd have to probably go back to important info part 3 with naming. This is not really popular in AP chemistry as far as naming and writing formulas, but it's still a good skill to have for AP chemistry. So number 6, I kind of did a lot of the legwork here. It says calcium carbonate. Calcium carbonate's a polyatomic ion. And so if I think polyatomic ion, I think ionic compound. I need charges. Calcium is 2+, carbonate's 2-. That gives me CaCO3. Decomposes. Remember, I said earlier that decomposes is my arrow. Right? So decomposes could be break apart, arrow, to form calcium oxide. Again, calcium is a metal. Oxide's a nonmetal. This is an ionic compound. So I needed to think about charges. Calcium 2+, oxygen 2-. They both have the same number but opposite in sign, so I only need one of each. That gives me CaO. And then carbon dioxide is molecular. It's got that di in the name. That means I must have a Greek prefix, and so this must be molecular. They're 2 nonmetals, and so I could write them as is, CO2. Done. And then I drew each particle diagram, CCO3, CaO, CO2, but I was in luck because it's already balanced now. There are 3 oxygens here and 1, 2, 3 on the product side. There's 1 carbon here, and then there's 1 carbon here, so we're good. There's 1 calcium on the reactant side, and there's 1 calcium on the product side. We're good. This was a 1, 1, 1, or you don't need to include 1s in your coefficients. I'm going to end this little extra help with doing zinc reacting with copper 2 nitrate in number 9. So it says zinc. Zinc by itself, I could just write Zn. So I'll say Zn reacts with copper, Roman numeral 2, nitrate. Well, if I think of nitrate, that's a polyatomic ion, NO3-1. Copper 2 means copper 2+. If I do and use my skills from the important information part 3 and do the crisscross method, copper 2 nitrate will look like this. I'll need 2 nitrates for 1 copper. And it will form, this is where they're produced, form zinc nitrate. Well, zinc nitrate, nitrate's -1 again. Zinc is a +2 charge. +2, zinc is always +2, and that is something that I mentioned in previous notes. So this is going to look like the copper nitrate. Boom. And then we got copper by itself, plus Cu. All right, let's make sure it's balanced. I want us to do this one because I want to talk about the nitrate. Let's make zinc shaded. Let's make copper unshaded. And for the polyatomic ion nitrate, instead of me drawing 1 circle with 3 circles, I'm just going to consider the nitrate a square. You could treat polyatomic ions as their own entity. Polyatomic ions as one big ion. So you can make them have their own shape, and it's going to simplify your drawing. So now this becomes zinc, copper with the 2 nitrates, zinc with the 2 nitrates, and then copper. And then would you look at that? Another example of I only needed 1 and 1, so my zincs are good, my copper's good, and I have my 2 nitrates. So this is just 1, 1, 1, and 1. Isn't that nice? All right, so that is all for this first lecture. You didn't have to listen to the last 5 to 10 minutes there. There was only extra if you needed it. Hopefully, if you came back after watching the first lecture, this was super helpful to you. And again, if you have any questions or concerns, feel free to reach out. I definitely have many more supplemental videos if you need to see more practice or you need to see this again in a different way. I could definitely share that with you.